All right, so in this example, we keep going, and we are following what we did in the previous video in 2a, example 2a, where we were looking at the solution of that problem, x squared plus epsilon x minus 1 is equal to 0. And so what I would like to approach now, instead of using the expansion method as we used before, I would like to just quickly touch on another method, which is called the iterative approach or iterative method. And see how this method works. So the iterative method is a way to provide an iterative method, of course, an iterative sequence that would provide, as we iterate, better and better estimates of the solution. That's something that is quite close to what we know from numerical techniques. All right, it comes closer to numerical methods. What you have learned by using various numerical methods to solve algebraic equations, for instance. And so the iterative approach requires to keep on the left-hand side the dominant term in x. And the dominant term in x, in this case, this is x squared. Why? Because this is a small number, so we need to put it on the right-hand side. And if we want to make an iterative method, we're going to keep on the left-hand side as few terms as possible, so that we can, in a very simple manner, write this iterative sequence. And how do we write the iterative sequence? We're going just to write that here. This is what we obtained at iteration I plus 1 on the left, while on the right we have everything that was obtained at the previous iteration I. So we just need to initialize the process or the sequence. And so how do we initialize in this problem, which is a regular problem? It's not too complicated, especially because we could use the solution of the unperturbed. So we're going to use either x0 is equal to 1 or x0 is equal to minus 1. And that would provide, or that should provide, two different sequences. I'm going to just pick this as an initial start, as a start for the following derivation, just to illustrate how it works. But of course, you could do the same, and it's left as an exercise if you wish to work a little bit on that, and have another example for you. You could start from the other value, x0 is equal to minus 1. And then we just iterate. That's just easy as it is. We're gonna end up with x1 when I is equal to 1 is equal to square root of 1 minus epsilon x0. I use the plus here in front of the square root because I do expect that x1 will remain in the neighborhood of x0, which is positive. All right, so if you do the same exercise starting from minus 1, you would need to keep a minus here in front of the square root. Okay, that's a good exercise. Do it just to practice a little bit later. If we write the series expansion for this, then we have 1 minus epsilon over 2 plus terms that are of over epsilon square. All right, because we are at the first iterate, we are not supposed to keep terms that are going after epsilon. All right, so we can truncate x1 and say, okay, if we want to have a better estimate than the original starting value here, if you want to have a better estimate is that. Okay, so we can now just keep going, and if we want to keep going, then x2 is the square root of 1 minus epsilon times x1, meaning we have the square root of maybe let me just put it in a different manner. Epsilon x1 over 2, that's the series expansion of the square root, minus epsilon square x1 square over 8 plus terms of order epsilon to the third. And now let me just substitute here x1. So we have 1 minus epsilon over 2. Of course, at order epsilon, we haven't changed anything. Plus epsilon square over 4 minus epsilon square over 8. And then I dropped a few more terms, which are of order 3. And so we have 1 minus epsilon over 2 plus epsilon square over 8. And what do we see here? We see something like this, which in fact corresponds exactly to what we had in the previous expansion. So when we used the expansion method, this is exactly what we obtained. And this is also the same as the Taylor series of the exact solution. All right. So the iterative method is also something that is quite straightforward. Let me just wrap up here. Iterative method. Straightforward. But requires series expansion. Although in the expansion method, we haven't used any series expansion at all. In this case, this is a series expansion, all right? And maybe more advanced, this is another series expansion. How does it work? Keep dominant terms on the left. How do we recognize the terms are dominant? Of course, when the problem is solved, then this is easy because when x, you see x is of order 1, which is also the solution of the unperturbed problem. So when the problem is regular, this is something we can guess in advance. Okay, remember from the previous video that we could guess in advance that x was either close to 1, either close to -1. You can use this quantity here, x is equal to 1, and check the order of magnitude of each term in that governing equation. So we could obtain that this is of order 1, this is of order epsilon, so much smaller, it should be brought to the right-hand side, and this is of order 1. Of course, we couldn't have kept the last term on the left. Okay, this requires a little bit of testing. If we had kept -1 of the left and pushed x squared and epsilon x on the right, there's no way you can write an iterative sequence here, right? Because -1 is -1, and there's no way you can write this. So that doesn't work. Okay. And so as a second comment or third comment or observation requires sometimes trial error to find best options. Okay, there will be a few more examples a little bit later in the chapter related to algebraic equations where we'll be able to discuss this. I hope that was clear. It was just a very simple and brief introduction to the iterative method. Left as an exercise now. Do the same for x0 is equal to -1, meaning that you're going to develop a sequence in the neighborhood of the negative root, and check that you obtain the same result as the result we had with the expansion method. All right. Hope you enjoyed. Keep going.